Okay guys, so the other video got cut off. Yeah, OneNote doesn't really like me all that much, but we're going to power through. So let's pick up with rational functions here. So rational function is going to be r of x equals some p of x over q of x. To find the vertical asymptotes here, we're going to go ahead and set the denominator, in this case x minus 3 equal to 0. We're going to solve for it. And if I add 3 to both sides, I should get x equals 3. So this is my vertical asymptote. Notice it comes in the form of x equals some constant. And if you remember from the parent graphs that I showed you guys, x equals some constant is just some vertical line. So this looks like it's in the correct form, right? Horizontal asymptote rules, let's not forget. If I have, all that I'm looking for, really all that I'm interested in, is the highest powered terms of any rational function. So if I had x squared plus 3x plus 64 or something, and then like this divided by 3x to the, I don't know, 6 or something, minus 9x cubed plus x plus 2. This looks really bad, but if I'm looking for a horizontal asymptote, all that I really care about is the highest powered terms in both the numerator and the denominator. So I care about this because 2 is bigger than 1, and this is x to the 0, so that's definitely bigger. And then I have 3x to the 6. Well, 6 is bigger than 3, and it's bigger than 1, and it's bigger than x to the 0. So this 2 and this 6 are the largest terms. These are my n, and that's going to be my m right here. So in the example I just made up, if I have x squared, so if I have like, this is really going to be 1x squared divided by 3x to the 6th. We'll notice that the top, right, n is going to be less than m, right, or the bottom is bigger than the top. So if 6 is in fact greater than 2, then I know that I have m is greater than n. So if m is greater than n, I get this particular case scenario. So I know my horizontal asymptote for this one is going to be like y equals 0. Now for the actual example that we have going on, let's see if I can't delete something. Let's see if it wants to play nice, guys. Are we going to wait? I think we can get it to go. Maybe. So difficult to do this. I just wanted to demonstrate the point. So let me erase this real fast if I can. Almost. So let's it's kind of going away. All right. Almost, guys. Go away. All right, cool. All right, so I think it's going to work. And for the example that we have, is 2x plus 1 over x minus 3. So 2x, what did I say? That's horrible. 2x plus 1, and then x minus 3. So x minus 3. What we'll notice here is that we have the highest power term is going to be 2x here, and on the bottom it's just going to be x. So in this case scenario, this is x to the first and x to the first. And when we have the power of both the numerator and denominator equal, that's what this case is, then we take the coefficients. This case, it's a 2 over a 1, so it's just going to be y equals 2 over 1 or y equals 2. All right, so this is going to be our horizontal asymptote for our particular rational function that we're working with here. And how do we find our x-intercepts? Well, set y equal to 0, so we'll take 0 equals, and then this is 2x plus 1 divided by x minus 3. And we just need to solve this. So we'll take our x minus 3 and multiply both sides by that. X minus 3 here. And 0 times x minus 3 is 0. 2x minus 1. And if we want to solve this, this is plus 1. So we want to solve this, we're just going to subtract 1 from both sides. I get negative 1 equals 2x, so now I get negative 1/2 equals x. And so I get a negative 1/2 here, comma 0. This is going to be my x-intercept. And on the other hand, I get my y-intercept. This is when x equals 0. So if I have f of 0 here, I get 2 times 0 plus 1 over, and x is going to be 0 again, minus 3. So f of 0 equals, this goes away to 0, this goes away to 0, so I get 1 over negative 3. So f of 0 equals negative a third. And what my y-intercept now will be is when x is 0, y is negative 1/3. And this is my y-intercept, guys. That's how I find it. So talking about even and odd functions real quick. So an even function, basically. An even function is, alright, so an even function looks like this. If I take f of negative x, it'll equal f of x. It has y-axis symmetry. So a good example of this is just a parabola like this. I can fold it directly over the y-axis. Alright, that's exactly what my example here looks like. So example, f of x equals x squared. So if I take f now negative x, this is going to be negative x squared. This is just negative x times negative x. So this is going to be, I can basically get rid of both of these negatives, right? Negative times negative is a positive, and now I'm just left with x times x. So x times x is x squared, and I know x squared is equal to just f of x, the original function. So this says that if I take f of negative x, this guy right here, it actually is the same thing as the original function f of x. This is my test for a function being even. So I've just shown that f of x, or if f of x equals x squared, that is even. And on the other hand, if I take f of negative x, it's going to equal negative f of x. This is odd. Odd functions have origin symmetry. So this kind of looks like this. It means I can fold it over the x and y axis, both of them. All right. And what this will do is if I take f of negative x here, this is negative x, this is cubed, this is negative x times negative x. And this turns into negative x cubed. And I know x cubed is just f of x. So negative x cubed must be negative f of x. And if I take f of negative x here, this is going to be equal to negative f of x. And that is exactly what the test that I gave you up here says about something being odd. So this is what I'm looking for. And if we want to use these tests to figure this thing out, hey, is this thing even or odd? Let's go ahead and take a crack at this. So we have f of negative x. This equals 2 times negative x plus 1 over negative x minus 3. And this is going to be equal to, looks like negative 2 x plus 1 over negative x minus 3. And this clearly is not equal to f of x. This is not the original function I have here, so it's not even. I can pretty much tell you that right now. And if I were to try to factor out a single negative 1 out of this thing, from either the numerator or the denominator, like, I'm not going to be able to get a negative f of x out of this thing either. So it's not going to be that either, so it's not odd. So what this tells me is that this thing is neither even nor odd. That's what this tells me about our particular function here. All right, so it's possible for it to be neither as well. So there are three options: even, odd, and if it doesn't check out to be even or odd, then it has to be neither. So it's not symmetric with respect to anything. It's not even or odd. Okay, horizontal versus vertical line test. Let's not forget the horizontal line test. We just take a horizontal line, draw it through a function. If it crosses between 2 points on our graph somewhere, we know that this is not a one-to-one function. All right, so it's really nice if they ask you this in the test. It's like super straightforward, and it's like 3 points. Horizontal line test asks, hey, is it one-to-one? If for another example, if I were to have a graph that looked maybe like this, like a cubic, like y equals x cubed, then I can draw a horizontal line anywhere I want through this, and it's only going to touch at one particular point anytime that I actually draw it. This would be 1 to 1, for example. All right, so if it touches in more than one place, not 1 to 1. If it touches in only one place, then yeah, it's 1 to 1. The vertical line test asks, hey, is something a function at all? And we just take a vertical line, draw it through here, and if it touches in more than one spot, then it's not a function. So this guy is not a function at all. Like, this thing is not a function. Now, if I wanted to, on the other hand, I could take, let's say, a parabola like this. I can draw a vertical line down anywhere. If it crosses through just one and only one point taking the vertical line test, this is, yes, this is a function. All right. So we also have inequalities. So if we have an inequality, let's not forget, I went ahead and factored this out for you already because I'm going to save time. We talked about how to factor, but let's say we got to x plus 6 and x plus 8. Let's go ahead and find out what our zeros are. I get, this is x plus 6, and I get 0 equals x plus 8. If I subtract 6, I get negative 6 equals x, and I get negative 8 equals x. I'm going to go ahead and draw a nice little number line now. And I'm going to take negative 8 here, and I'm going to take negative 6 here. And if I took some test values, and let's do this. If I took some test values, and let's take something to the left of negative 8, maybe negative 100. So if I take negative 100 plus 6, and I multiply this by negative 100 plus 8, all right, I know that this is going to be a negative value here, and that this is going to be a negative value here, right? Like, this is obviously going to be like negative 4 for this, and then it'll be like negative 92 for this. So negative and a negative. That gives me positives here. If I take a value between negative 8 and negative 6, perhaps negative 7, then I get negative 7 plus like this. So I get negative 7 plus negative 6, so negative 1 here. And then this other one's going to be a positive 1. So negative 1 times 1, this is all negative in between here. And then if I take some other value to the right of maybe 6, negative 6, let's make it easy now. I'll take 0. So 0 plus 6, 0 plus, what is it, 8? And this is 6 times 8. It's positive. It's 48. All plus. And what am I asked for? Hey, where is f of x strictly greater than 0? So I want all the positive intervals. And the positive intervals here are going to be from negative infinity up to negative 8, non-inclusive, because I'm not setting it equal. It's not this sign. It's strictly greater. So that's why we're using the soft bracket over here. That's why we have this soft bracket right here. And then it's going to be union, negative 6 up to positive infinity. So this is where my function is strictly greater than 0. So this is where I have, whoa, what was that? So this is where I have f of x is strictly greater than 0, okay? All right, continuing along, the difference quotient. So they might give you this formula. I don't remember, they might not. I think they give it to you, but review it just to make sure. Let's go ahead and do the difference quotient real quick. So if we have a difference quotient, we're just going to go ahead and take the difference quotient to 2x plus 1. And let's go ahead and say the first thing is if I have f of x plus h. So what is f of x plus h here? F of x plus h is going to be 2 times x plus h plus 1. All right? And f of x is just 2, and this is x plus 1. So if we apply the difference quotient formula, what we have up here now, it's going to look like f of x plus h. That's going to be this bit right here. So this will be 2x plus h plus 1. And minus f of x. So minus f of x is going to be 2x plus 1 now. And hard bracket there. And this is all over h. And so let's go ahead and do this. And be really careful. Put this in brackets just like this that I have here. And we're going to do that because we want to distribute this negative to both terms. And if you have more terms, you do it to more terms. So this is going to be now 2 times x plus 2 times h. That's just distributing these, plus 1 minus 2x. That's this minus sign being distributed to the 2x. And then minus 1. So minus 1 here. This is all over h. And now I can start canceling. So I get a negative 1 here and a positive 1. these can go away. Negative 2x and a positive 2x, this goes away. And I'm just left with 2h over h. H's go away, I'm left with 2. This is the answer. And it makes pretty good sense because the slope of this thing was 2. And looks like the difference quotient was 2. So it's not always going to turn out to be this nice and simple. I just picked a really simple example so you kind of remember the idea of the setup, all right? But yeah, so this is the setup of the difference quotient, all right? Last but not least, complex numbers. So complex numbers, remember, they're sometimes called imaginary numbers, and the first thing is I equals itself equals I, all right? That's this. I squared happens to equal negative 1. I cubed, how do we get I cubed? Well, I cubed is just, if you remember exponents now, I squared times I, and this would be I squared is negative 1 times I, because that's what it is, so this turns out to be negative I. So that's why I get I cubed is negative I. And I to the fourth, if you think about this, I to the fourth is just I squared times I squared. This is negative 1 times negative 1, which is 1. So that's why we get I to the fourth equals 1. And typically what they like to do with this is they'll give you something like I to the 18th or something and ask you, okay, what does it equal? You kind of have to remember exponent rules for this. And all we'll do is we'll say I to the fourth times I to the fourth times I to the fourth times I to the fourth. If you remember exponents, we have a base of I. And we have essentially, it's going to be the power of 4 times 4 times 4 times 4. So this is basically I 4 plus 4 plus 4 plus 4. But this only gives us 16. So let's go ahead and tack on an additional 2 to make 18. So now I squared. So this would be like plus 2. So we know this is I to the 18, but looking at it in terms of this, we can actually kind of figure out what this really equals. So I to the 18 equals, well, what is I to the fourth? It's just 1. So this is 1 times 1 times 1 times 1 times, and then what's I squared for this last bit right here? I squared we know is equal to negative 1. So this is going to be negative 1. So all these ones multiplied together gives me 1. The last one here is going to be negative. So I to the 18 happens to equal negative 1. And this is the solution to how to find that. This is the end of my review. That's all I have for you guys. It's been a pleasure. It's been nice working with you guys. Good luck. Hope you guys do well. Take care. Stay safe. Crush algebra. If y'all see me sometime, holler. Take care, guys. Bye.